Welcome to the GOTO Podcast. In this episode, Adam Tornhill, CTO at CodeScene, explains the link between how organizations write code and how teams work together. GOTO gathers the brightest minds in the software community to help developers tackle projects today, plan for tomorrow, and create for a better future. Stay up to date with the latest in tech through GOTO's top-rated events, held online and in person in cities like Chicago, Amsterdam, London, and Copenhagen, and by subscribing to the GOTO Conference's YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
Hello everyone, welcome to the GOTO Book Club. I am Sven Johann, I work for INNOQ. I like improving systems, I like to talk about it, I like to teach it, I like to write about it. And today I have as a guest Adam Tornhill. Adam, would you like to introduce yourself?
Yes, sure. Thanks, Sven, and thanks for having me here. So I'm Adam Tornhill. I'm a programmer and psychologist. Been working in the software industry for 25 years. And I spent the past 5 years building a platform called CodeScene, working with code analysis. I'm also the author of a couple of books, and I like to think that the best known books are Your Code is a Crime Scene and Software Design X-Rays.
Yeah, actually quite an interesting combination. How did it come that you studied computer science and psychology?
So my experience was I started to work in the software industry in 1997. And after a couple of years, I kind of noticed a pattern that succeeding with software at scale is incredibly hard, right? I saw one software disaster after another. So at some point, I just want to try to understand why is it so hard to write good code? And I kind of decided to seek the answers within psychology, because psychology, I think, has a lot to offer to us in our traditional technical field. You know, psychology is about how we think, how we reason, how we solve problems, and also how we collaborate with others. And originally, I just signed up for one semester, but, you know, psychology is really, really fun. So after that semester, I thought like, okay, let's dive into one more topic and then one more topic. So I ended up spending 6 years at the university. So I took my degree by accident, more or less.
Oh, okay. Yeah, I agree. I did once a Coursera course, like an introduction to psychology. Basically, it was only the most famous psychology cases, and it was also very fascinating. But I stopped after one semester. So, but yeah, nice. And I think this rare combination brought, to me at least, a totally new thinking about improving systems. So before I read your first book, Your Code as a Crime Scene, I use tools like Zona, and I don't think that Zona is like a bad tool. I really like it. It's it helps you seeing problems with your code, but it makes it really hard to prioritize your work. If you run like a Zona analysis and it tells you have 3 million findings and your technical debt is 2,000 years, it takes 2,000 years to pay it back. It's just not helpful. I have to invest a lot of time to understand what's really important. Yeah? And also the tool, even if I figure out what's important, the tool cannot really help me. But okay, that's how we worked in the past. But then your tool came along, and I think it made it really easy to prioritize. And maybe we should talk about the thinking about the prioritization in that one. So you called the type of prioritization, if I say that correctly, a behavioral code analysis. Is that correct?
Yes, that's correct. And it's pretty much about taking my psychology background and putting on top of the technical work that I do. So the whole idea is that I agree with you that static analysis, to me, it's also a valuable practice, right? It's something that works very well, I think, as a low-level feedback loop when writing code. But static analysis, like you point out, has this property simply that it treats all code as equal, right? Because there's no such thing as a business priority when you just look at the source code. And that leads to having thousands of findings. So what I do instead is that I look at how do we, as a development organization, how do we interact with the code we're building? So in practice, that means looking at things like version control data. You might look at things like Jira data and so on, because then you can kind of calculate the impact of each one of the findings. So what that does basically is that it gives you a window into all those code quality issues and tells you that this is what's important, and this might be problematic long term, but we can most likely live with it for now. So that's like one of the things. The other thing that I kind of noticed with static analysis is that once an organization grows beyond, I would say, just a handful of people, then organizational factors like coordination between different teams, team coupling, key personnel dependencies, knowledge distribution, all that kind of stuff tends to become at least, maybe even more important than any technical properties of the code. And static analysis was simply not designed to help us with those aspects, right?
Exactly.
So yeah, that was pretty much why I decided to call it behavioral code analysis. It's more about the behavior of the organization rather than the code.
When I tried to prioritize, I also thought about our customers. How many, for example, codes which is used very often or executed very often because of customer use. Would that also be part of an idea to prioritize by how customers are interacting with the system?
I mean, it could definitely be an aspect, right? So typically, software is interesting because it has these power laws everywhere, right? And so you look at code and it's like 80% of your code is never touched. You look at your feature set and it's most likely the same thing, right? That most customers use a smaller subset of your features, right? Mm. So clearly there is a priority aspect there as well.
For me, it was easy to convince, for example, a product owner to, for improving code when I could say, this is part of the 80% usage pattern or something like that. Okay, and then, you wrote the book, Your Code as a Crime Scene, and then, and now you published a new book, Software Design X-Rays. What was a new learning you had to write a follow-up book?
Yeah, so Your Code as a Crime Scene is a book I wrote in 2014. And what I did back then was basically I captured a number of techniques that I had used myself in my previous life as a software consultant. So it's techniques for prioritizing technical depth to communicate with non-technical stakeholders. It's stuff that I found useful myself. So I published the book and it got quite a lot of attention. And I kind of realized that if I want these techniques to become mainstream, then there has to be some good tooling around them, right? So shortly after publishing that book, I founded CodeScene, the company, to kind of build those tools. And as part of those early years with CodeScene, I was fortunate to work with so many organizations across the globe. So I worked with organizations on using different technologies of all kinds of scale. And I learned so much about that. And I basically, with Software Design X-Rays, to try to reflect those learnings. How well does this stuff work in practice? And even more important, how do you act upon it? Because information is only good when actionable.
Yeah.
So that was the main motivation.
Yeah, that was also, I like a lot about the book, actually about both books, but the Software Design X-Rays, it usually has a recommendation, what to do with those findings, but we can dive into that a bit later. So the first part is, and that's for me still the most fascinating part of your work, is hotspots and X-rays. So what is an hotspot?
So a hotspot is a complicated code that we also have to work with often. So it's a combination of technical factors like code quality issues, design smells, together with frequent development activity in that part of the code. So that's basically a hotspot. And the whole hotspot concept, it came out of my experience of using static analysis to try to prioritize findings. And like we spoke about earlier, I simply lack the priorities from the business side, right? And I also faced these challenges of communicating with non-technical stakeholders. Because very often I try to explain that, okay, the business presses for this feature, but maybe we should take a step back and improve what's already there so that we can implement it safely, right? And on time. And I found that those conversations, they were extremely hard to have because software, it simply lacks visibility, right? There's no way I can take my software system, pick it up and show it to my non-technical stakeholders. So at the same time that I was wrestling with these problems, I was also in the middle of my psychology studies, and I took a bunch of courses in forensic psychology. And that's where the hotspot concept actually came from. So I was inspired by a technique called geographical offender profiling. And geographical offender profiling, it's something forensics use, right? So what you do is basically you look at the geographical distribution of different crime scenes in a city or in an area, and then you calculate mathematically a probability surface that can kind of help you predict what's the home base of the offender, so you know which area to patrol and supervise. And when I learned about that, I think something just kind of clicked, because I kind of thought that, wow, what if we can do the same for software? What if we can take this large software system, get a probability surface onto it and say that, hey, these are the parts of the code that are very likely to change in the future too. And these are the more stable parts of the code, things like that, right? Then we could suddenly, we would get some real priorities on what needs to improve and where code quality is most important. So a very lengthy answer to a simple question.
Yeah, I think, you do that by let's say, combining static code analysis and mining software repositories. So code which has a lot of commits and is bad, that's kind of problematic, and we should work on it. And yeah, for me, it's so easy now to explain, let's say to business stakeholders, why this is important. Because technical debt, you have the metaphor technical debt. It lacks a little bit with financial debt, but still you can say, well, we have an interest and we have a principal we have to pay back. And what is actually the interest rate? And you answered the question. The interest rate on code, which is, so interest means I have to spend more time thinking on pretty bad code when I add a new feature, because the code is not ideal for implementing the new feature. And of course, if I have code which is really bad and I have to change it quite often, the interest rate is very high. So to me, it really it sticks to my mind. What is your experience with your customers? So I'm only one single person who is doing it rarely, but you do it all the time. So does that stick to, let's say, non-technical stakeholders all the time, or rarely, or how does it work for you?
Yeah, so that's an interesting question, and the short answer is that I have a good experience, which is great. Otherwise, I wouldn't have food on the table, right? So I'm kind of happy about that. And my experience is that non-technical stakeholders, because these techniques were originally, I kind of targeted engineering organizations and occasionally, as a bonus, non-technical stakeholders. And my experience is that non-technical stakeholders, they like it, because a hotspot analysis sends a positive message. It basically tells you that, no, you don't have to fix all technical debt, right? You have to fix this debt. That's really critical, but you can safely live with this technical debt. You need to be aware of it, of course, but you don't need to pay it down now. So it's a positive message for them, because they're also wrestling with these long and short-term priorities. Like you have all these features that the business pushes for, and at the same time, there is some awareness that we need to improve things, right? So I like to think that's the main contribution.
Exactly. So it's what you say. You can improve. There is always something to improve. If someone asks me, we have a software system to improve. Yeah, there are a gazillion things to do. The question is, what brings the most value for your work? Because you always have, of course, opportunity cost. Yeah? And if I improve this, I cannot improve the other thing. And yeah, I think the hotspot analysis makes our not to do lists longer, and it shortens the to do list. What you're also doing is you have a trend analysis, and I like trends. If you're good and you have a negative trend that tells you have to improve something, and also if the other way around. How do you analyze those trends? So how are you doing it?
Yeah, so to me, trends are what makes all the data truly actionable. Because I very often meet organizations, they might be struggling with something like a legacy code migration, or they have an existing system that they're earning money on, they need to continue to be able to maintain it. And you have this constant pressure for new features, right? So I always tell them that, to manage technical debt, step 0, the absolutely first thing to do is to avoid taking on more debt, right? So simply put like a quality bar on what's already there and make sure it doesn't get worse, no matter where you start from. And I think that's, again, something that resonates with managers and technical leaders, because I'm yet to meet anyone that tells me we want our code to get worse. You never hear that, right? So it's actionable. So that's the first thing. The other reason I like trends is because they carry so much more information than any absolute values. So for example, in CodeScene, we have this concept of code health, right? It's a metric that goes from 10, healthy code that's easy to understand, low risk, all the way down to 1, which is code with severe maintenance issues. And let me say that I point you to a hotspot with a code health of 5. Is that good or bad? Well, if that hotspot had a code health of 8 the week before, then it's disastrous, right? Because it degrades rapidly. It's something you need to act upon now. But on the other hand, if that hotspot had a code health of 2 the week before, then it's a dramatic improvement that needs to be celebrated, right? So trends carry this information, whereas absolute values don't.
So when I used CodeScene, for me it was like not a one-time thing, but when I see my first analysis, I'm like, okay, now I see the red parts. So you have those parts which are bad code, changed often, and then to me it triggers the thing. Okay, all the red things, those are the ones which should be on my to-do list. But how do I see, let's say, parts which are good, but they are getting worse and worse, but they don't show up like red on your on CodeScene. So how do I figure out negative trends which are not horrible yet?
If I remember correctly, I had a chapter discussing this in Software Design X-Rays. I think it's the last chapter where I talk a little bit about how you can use the trends as an early warning system. And I think this is really, really important. And it's so important that we spend a lot of effort building it into CodeScene as well. So we integrate with things like pull requests and build pipelines, right? So you can kind of get an alert when things like that happen. And I think it's vitally important because one thing I learned that actually surprised me was that I like to think like so many other in the software industry. We have this idea that code starts out fine, right? And then we have the pressure of the business and the code kind of degrades over time. But that's not what's happening in general. What's happening in general is that if you find a module with quality problems, low code health, most likely those problems have been introduced very, very early on, often in the first version of that module. And once a module degrades in code, that tends to be like a self-amplifying loop, right? Because the hurdle to refactoring is large, so instead we kind of squeeze in more complexity, and it gets worse and worse. So using this kind of information, you can actually set different quality gates and say that for new code, this is the minimum level of quality or health that we accept, right? And then you can use it as an early warning system, which allows you to prevent a ton of future problems.
Yeah, so if the bad code is, I mean, to me, it's also surprising. That was a surprising insight from the book that bad code is more or less from the beginning bad. But you also wrote that bad code usually stays bad. So, it's bad, you fix it, but then it's coming back. Why do you think that's the case?
So I think there are several reasons, right? So it's one of the things I noticed earlier on, shortly after writing your code as a crime scene, when I started to work with this, when I started to work with organizations. And I kind of figure out that, we found these really, really problematic hotspots. And then you start to look at the trends and you saw that these hotspots, they have been problems for years. And at first, I kind of couldn't explain that. So why hasn't it been refactored? And there can be multiple reasons. But one reason that I think is very common is that those really problematic hotspots, there are some code quality issues that kind of tend to lead to organizational problems as well. So if you look at the different behavioral code analysis, you look at the main contributors and you look at how fragmented the contribution activity is to that file. So you look at a purely human perspective. And you will most likely see that that code is not written by one person. It's in a large organization, it might be, written by 50 or 60 contributors. And what that most likely means is that, no, you don't have 50 people that know that code. You have no one that actually knows it, right? Because everyone has their small piece of information and the original authors might long be gone. So it might often be that we don't really understand the problem domain well enough in that code. We might not understand the solution well enough. And that kind of, again, raises the hurdle for refactoring it. And in particular, we don't feel any kind of ownership for us as a team, right? So and that makes us much, much less likely to invest the risk into refactoring it. So that's my hypothesis.
I mean, what does it mean for an organization if I have that, if I have many people working on the code? You said the problem is not well understood. What are you recommending companies to, let's say, to fix that bad code, which is like not going away? What can you do to make it happen that it doesn't come back?
So I like to think that the single most important thing you can do is to get situational awareness so that everyone in the organization, engineering, business, everyone knows where the problems are, how severe they are, and what they actually mean to the business. Because once you have that awareness, the next steps tend to be not easy, but doable at least, right? And then it, of course, depends on what kind of issues you have. So if you have things like, so that's another behavioral code analysis technique that looks at something called system mastery, for example. And system mastery is not a technical property. It's about how much of the current code is written by the current team. Because I often see this as well, that social and organizational factors like system mastery tends to influence how we perceive the complexity of code. So we kind of tend to overestimate the complexity of unfamiliar code. And that means you can hear complaints about, hey, this piece of code is overly complicated, it's a mess. Whereas in reality, it might simply be that the team never had a chance to get onboarded properly and understand the domain and the solution. So if you have that situational awareness and knows what your actual problem is, then you can also address it, right?
When you said a lot of people, if a lot of people work on the code, that was also a finding that when you analyzed all sorts of systems, that you have code which is, let's say, rarely touched, and that that's not a problem. Then you have code which is often touched only by a handful of people, like 1 or 2 or 3 people. And then you have the code which is changed often by many people, but also, it's not immediately changed. It's changed from time to time, and that puts another burden on it. If we have a mental model on the code, because we work very often with it, we usually, don't introduce bugs. But if we rarely touch code, we are not 100% familiar with it, and then we introduce new problems. That was also something I found quite interesting.
Yeah. So I definitely think that it's a very common problem that I see, that you get lots of contributors in a particular piece of code. And if that code is also a hotspot, then the situation isn't particularly good, because what it basically means is that even if I write a piece of code myself today, then look at it 3 days later and it looks completely different because, 5 other people have been working on the code. So it's virtually impossible to maintain a stable mental model. And what's so fascinating about this is that very, very often it's about technical properties of the code that kind of lead to organizational issues. So what you will often see is that when you have that kind of code that attracts many different contributors, it's probably because it has good reasons to do so. It's typically a module that's very low on cohesion, meaning it has tons of different responsibilities. So consequently, different teams working on different features, they all end up in the same part of the code because it kind of ties everything together, right? So the solution there, it's a problem that you simply cannot solve with a reorganization, because then you will introduce other bottlenecks, right? So the proper solution there would actually be a technical refactoring or redesign, right? Which will kind of improve the organizational fit. And this is one of the things I found fascinating myself.
Okay, switching a bit the topic, going to the X-ray. What is an X-ray?
Yeah, so an X-ray is basically a hotspot analysis at the function level. And the reason I started to develop the X-ray analysis was because after writing your CodeScene scene, when I analyzed all these systems, right, I kind of noticed that the hotspot that I tend to find that are most problematic, they're typically really, really large files. We can speak about, it could be thousands of lines of code, occasionally tens of thousands of lines of code. It can be extreme cases like that. And even if you kind of take that large system, you narrow it down to a single hotspot and say, hey, this is your biggest problem. If I go to a client and say that, rewrite this code, it's only 20,000 lines of code, they're not going to be happy, right? It's not actionable. So what an X-ray analysis does is that it takes that complex hotspot, parses it into separate functions, and then it looks at the Git log. Where do each commit hit over time? And we kind of sum that up, and you get hotspots at a method level. And that's what I've been using successfully as a starting point to, prioritize refactorings in large complex classes and modules.
Yeah. If you tell someone 20,000 lines of code class is a problem, they would say, well, we figured that out by ourselves. Yeah, I think, it's also, it's used in many places. So if you, for example, Simon Brown has the C4 architectural model, and there you also have this kind of zooming, or Gernot Starke has ARC42. We start from a very abstract view, and then we dive always deeper. It's like Google Maps. When you look at the map, and then you can always go deeper and deeper. So you're not lost in details. You can navigate quite nicely, and I think that's quite a good idea. Yeah. You use very simple metrics. So when I look at a typical tool like Sonar, there are lots of metrics which tell me, this is a problem. And I think you only use lines of code of a class or a method, right? And intention from lines. So no dependency analysis and things like that. And this is based on some research, and could you please explain why you focus on very few metrics and why that's still super powerful?
I like to think we evolved that a lot over the past years, but basically the thinking process is that if you look at the research, you will see that a simple metric like the number of lines of code, which it's a horrible metric, right? It's really, really bad. The thing is that most other metrics are just as bad. And lines of code is intuitive, it's simple to calculate, simple to reason about. So that's basically where I started out, that we need a complexity dimension for hotspots. Let's use lines of code. And it surprised me how far that actually gets us, right? It takes us really, really far. One thing I learned after writing your CodeScene scene is also that lines of code, it works well, it correlates with most other metrics, but I kind of also learned that at some point you want to dig a little bit deeper and provide some actionable advice around what type of refactorings do you need to do and stuff like that. So what I've been working on a lot over the past year is to add different static analysis techniques into a behavioral code analysis via CodeScene, right? And what we try to do is to look more at the design level, like identifying brain methods, dry violations, the stuff that really, really matters for maintainable code. So these days, I might still use the number of lines of code, like an initial visualization, right, to get situation awareness. But when I dig deeper, I typically use this more elaborate set of metrics. So I hope that makes sense.
Yeah, I'm just wondering, because my understanding was, when I look at a hotspot and I dive deeper, that the hotspots show me, so there are distinct metrics. So when I look at a hotspot, I look at lines of code and, let's say, a cyclomatic complexity represented by intention. But clone detection, violating the try principle, that I was not aware that this is also part of the hotspot. So yeah, what is actually change coupling?
Change coupling is a very, very interesting software analysis technique. It's interesting because it's something you cannot do just based on the source code. So if we talk about coupling in general, as a developer, we typically refer to coupling as some kind of dependency, right? You have some piece of code over here, it uses some piece of code over here, they depend upon each other. Change coupling is different because it's more about logical dependencies. So in a behavioral code analysis, you measure how the organization interacts with the code they're building. So in change coupling, we pick up patterns in, it could be anything from the Git log to more advanced architectural analysis, where we pick up patterns in Jira data and stuff like that, and figure out that each time I need to modify a piece over here, I have a predictable modification in the module over here. So there is some kind of logical dependency between them. And using change coupling, we can get a lot of interesting feedback on how well our architecture supports the way we work with it. So that's the short description.
Yeah, I mean, we all know the situation where we change, let's say, a piece of code, and then, okay, now we have to change 5 completely different unit tests because of some copy-paste coding. How does a change coupling relate to clone detection?
Basically, the original challenge I had was that this was way before CodeScene, way before I wrote the book. I was working as a software consultant, right? And I was working with a team that were very heavy on test automation. And the problem they had was that they got a lot of flaky tests, right? So this was automation at the system level, at the application level. And the problem was, of course, that as a developer, you kind of you pushed some changes, you updated some tests, and then you had 3 other tests failing because they kind of also depended upon some logic. Now, using change coupling, what we could do was we could first of all visualize the changes, right? So we could figure out that you make this tweak in the application code, and now you have to modify this whole cluster of files, right? So that could kind of highlight the problem. But to make it actionable, we wanted to drill deeper and figure out, is the reason that we have this change coupling, is it due to drive violations of the don't repeat yourself principle? And adding copy-paste metrics on the top of this proved to be really, really useful. And to me, change coupling is an excellent way of benefiting from clone detection tools and copy-paste detection tools. Because the main problem with copy-paste is that there's simply so much of it, right? So you look at the research and you see that there's like somewhere between 5 to 20% of all code out there is duplicated to some extent. And not all of that application is bad per se. So using change coupling, it kind of gives us a window into those massive amounts of duplicated code, and we can kind of figure out that, okay, these are the software clones that are actually expensive to maintain, right? Because we have these predictive modifications.
I mean, you had it in your book. I mean, a clone is not an exact clone, right? So there is usually you copy something and then you paste it and then you change this tiny little bit. But of course, if one thing changes, you have to change all the rest. Clone detection tools also find those, like half-baked copy-paste, edit pieces of code, right?
Yeah, that's right. So I think that a clone detection in software it's a pretty old technique, right? It's something that's been in industrial use for almost 3 decades. But again, I think that simply the sheer amount of duplicated code makes it very hard to act upon it. Because to me, I think one of the main problems with copy-paste is that we as developers, myself included, we are kind of conditioned to despise copy-paste. We have learned over and over again that it's a bad thing to do, right? The problem is that it's simply not true as a general statement, because let's say that you have a piece of code here, right? You copy-paste it, and now these 2 copies, they evolve in completely different direction. One could very well argue that copy-paste was a good starting point, right? Or maybe you duplicate some code and you never need to touch it again. It might not be ideal, but is it really a big problem, right? So the problem starts when we actually have to make those when it copy-paste, when it kind of drives our behavior in a negative direction, right? So we have to make those predictive modifications. It's easy to miss to update one of those clones, right? And that's why I think this combination of change coupling and clone detection really, really adds value in our daily work.
Yeah, I agree that it's not always bad. I tend to, do a first time copy paste edit, but when I do it the second time, then, it's time to say, okay, now I need an abstraction, because, introducing an abstraction to, for one time thing, Dan North, he once said, try is the enemy of the decoupled. That's something I'm wrangling with, and but in terms of microservices, for example, or it doesn't even have to do microservices, just different, completely independent modules. When you see that, whenever I change something far over here, I have to change something far over there, even in a totally different repository, then things become a bit problematic. And I wonder, how do I find out if I have a problem? Because, maybe I only have like this one-time thing, as you said, or, it's a real problem. How can I find that out?
Yeah, that's a very interesting question, because I think the whole the incredible hype behind microservices over the past 5 to 6 years kind of flipped the whole architecture and design thing around a little bit, because there are definitely scenarios where you want to violate the drive principle, because loose coupling is simply more important, right? It's a more important capability than minimizing the amount of the application. At the same time, what you want to avoid is to have exactly the same behavior in two different places, if that's a behavior that's being frequently modified. Because if you have that, it could very well indicate that maybe you miss a microservice to take on that shared responsibility. That maybe it's a separate business capability, right? So what I do, there are two aspects to it. One is getting the data. How do we figure out change coupling across Git repositories? The second challenge is how do I act upon it? And I wrote about this in the book. So change coupling in simplest forms is based on finding patterns in the commits, files that change together over and over again as part of the same commit set. And that clearly doesn't work across repositories. So what we do there is that you simply look at the ticket system instead. Things like Jira tickets, Azure DevOps tickets, whatever, right? And see that if the commits reference the same ticket, then we know that they're kind of depending upon each other. And if it's happened often enough, then that's a very strong signal. So that way you can kind of, even across Git repositories, you can detect change coupling down to the function level, right? So this is something that's very powerful, and you can of course add clone detection on top of that as well, and then see, is this a drive violation that's desirable, or is it an actual problem that we lack some level of encapsulation or abstraction? And what I would say is that to me, it's a hard engineering problem, right? But the more challenging aspect is to make that decision, right? Do we live with this or do we ignore it? And what I tend to recommend is I use a general heuristic that I call the heuristic of surprise. So I simply visualize the change coupling, and then I take everything I know about the architecture and the problem domain. And any surprising coupling that I find is usually bad, because, surprise is simply one of the most expensive things you can ever have in a software architecture.
Yeah, rarely people are positively surprised.
Yeah.
It's always don't make your manager being surprised, because usually it's negative. But you wanna show the coupling. So how do you show the coupling? Is it? I mean, I remember from when I looked at CodeScene, and also when I remember the book, it's like I show two files, right? And then there is like the amount of coupling of those files and how often they change together, so to speak. So what's the thinking about this approach? Showing the files and the amount of coupling.
Yeah, so the interesting thing with change coupling and a lot of those other behavioral code analysis techniques that we talked about in the previous episode, like hotspots and that kind of stuff, is that they scale at different levels. So you can use change coupling at the function level, right? You can use it at the file level, and you can use it at an architectural level. And that's where I usually start when I pick up a system. I look at the different architectural elements, and they could be either different layers, they can be different components, or they can be microservices. And I simply figure out the change coupling between, let's say, the different services, right? So I typically visualize it. You have all your services like a wheel, and then you see the connections between those edges. And that's usually my starting point. And in my experience, because I've been fortunate to work with so many organizations across the globe at all kinds of scale, and I see several organizations are doing really, really good job with it, but occasionally there is a surprise. And the surprise is very often that even though you put all these efforts into defining proper service boundaries, right? We know about bounded context, domain-driven design and all that stuff, right? But the thing is that it's incredibly hard in practice because we basically have to be domain experts to do that, right? So the surprise tends to be that, hey, we're actually starting to build a distributed monolith, right? It's very easy to highlight that with change coupling, that when you change this service, right, you have a dependency to 5 other services, and then you look at the details, what kind of functions are coupled, and you often see that you implement a new capability here, a new business capability, and to pull that off, you need to query 2 different services and update the state in a third one, right? So that's the typical warning sign that I tend to find.
I can have from time to time, let's say, this coupling. As we said, maybe we have 2 code clones in 2 different services, and then we change it once, and that's fine. It just happened once, and that's probably not a problem. If we change it a second time, a third time, a 10th time, 100% of the time, we change those files together in different services. Is there any, let's say, recommendation when I should start worrying about those temporal dependencies?
So I find it very hard to give general recommendations in this area, because with hotspots it's usually quite easy, right? If you work on a part of the code a lot, and that part of the code has a high degree of technical depth, then it's very easy to say that, okay, we need to fix this, right? But with change coupling, it's so much harder because it kind of depends on the life cycle of the code base, right? If it's something you just got started on, there's probably going to be a lot of experimentation and learning going on. So I do expect a higher degree of change coupling and more complex change coupling, right? But I would say that anything beyond, let's say, in a more stable system, right, once the basic architecture is set, I would be worried about any change coupling that's over 20%. That would worry me.
Okay.
The other heuristics I use is basically that change coupling gets more expensive with distance. And what I mean with distance is, first of all, architectural distance. Like, are these 2 completely unrelated parts in theory, but in practice tied together? Then that might very well be one of those surprises. The other one is dependencies that cross team boundaries, right? Because that very quickly becomes expensive because the teams end up in all these coordination meetings, and they might have conflicting changes in their API and stuff like that.
Yeah, I can sing a song about those kind of problems. I think if you have different repositories and one team is responsible for that, okay, it's not nice, but it's still, let's say, it's manageable, and it's also, I would say, it's also easy to fix because it's one team, just a couple of people own the different repositories and can think about reducing or getting rid of that coupling. But across teams, that's going to be tricky. So what are some interesting examples from your experience on that problem?
Oh, I have so many. I'm not even sure where I should start. So I think one of the most common issues I've seen, and this used to be more common maybe a few years back, like 2-3 years ago, was that several organizations that I worked with, they kind of asked me, like, how should we organize our development teams, right? So we started out with component-based teams, right? Then we noticed that we had very, very long lead times, right, for new features, because you had to do these handovers all the time between change coupled components. So we changed to a feature team. And now we kind of noticed that our whole quality aspect just went south, right? Because suddenly we find that we have 10 different teams all working in the same parts of the code. So to me, it's a much harder answer because the organizational aspect always goes hand in hand with the software architecture, right? So you really need to balance these two. And if you want to have component teams, then I think a much better approach is what the team topologies people recommend, right? With stream-aligned teams. That's the only way I've found that actually scales, that you have the teams separated based on business capabilities, right? And that those business capabilities are reflected in the architecture. I really haven't seen anything else that works at scale.
Yeah, I was about to say, in the team topologies book, they have this quote from, I believe, Ruth Malan. If there is the software architecture, but there is also the communication architecture, and basically on, Conway's law. And if you don't care about, if you as an architect don't care about team setup and communication structure between teams, basically you give the architecture tasks to someone who cares, like a non-technical manager, right? And then you end up in those problems you described. Is there a way how to use those insights on a change coupling, on a, let's say, based on different teams working on the same code base to refactor teams towards those stream-aligned teams?
Yes, there are. And I like to think this is one of the most important contributions by behavioral code analysis and software design X-rays, and what we do with CodeScene as well, of course. It's that it brings visibility to the people side of code. And to me, I always talk about this like the grand tragedy of software design, that the organization that builds the code is invisible in the code itself, right? So using behavioral code analysis, you can actually visualize that. So you can show which team works where in the source code, right? And you can overlay that with change coupling information so that you can easily show those bottlenecks, right? That when we modify this service here, that team have to coordinate with 4 other teams, right? You can visualize that. And from there, it's mostly about domain expertise to figure out, okay, quite often it's not enough to just shift the teams around. Quite often you have to do some more fundamental change, and maybe those 2 different services or component, maybe they are actually the same component, right? So you need to merge them together. And occasionally you find that the organization simply lacks a team to take on a new responsibility. It's
kind of, let's say, the same pattern maybe we discussed the last time. So the last time, the hotspots actually create a not to-do list. You have so many problems, but with the hotspots, you get a focus on the problem. And here we would have the same. If you need to think about your team setup or your team topologies, to use the word, basically, I can look at those parts where many teams own a lot of the same code, and also where are teams actually quite distinct from each other in the code base. And I can use that one, like the problematic part, to look at where do we need to create better boundaries, team boundaries.
Yeah, and I think that's important, because the moment you're able to visualize that, then you can start to have a meaningful conversation between engineering and the business, right? Because in my experience, even with organizations that have a fairly high degree of team autonomy, right? A team can usually not decide that. They can decide what they want to do. They can decide what they want to do differently, but they cannot decide for the whole organization, right? We need some kind of buy-in. And being able to show that data really, really helps in my experience.
If you just say you have a problem or you have a feeling, usually people don't react to it. Yeah, in your book, you describe that you can test your architecture. Let's say architecture in terms of dependencies on teams. Like if you implement a new feature, how many people do you need to bring in one room to find out how, let's say, good or bad your real dependencies are, either your hard dependencies or your soft dependencies. So if I want to implement a new feature and I have to call like a big stuff event, I obviously have a problem. So what's your experience with those tests when you do those tests with your clients?
So my experience is that it's very easy to end up doing local optimizations, right? So organizations always they always know themselves that we have a lot of coordination meetings, we have a lot of sync meetings, right? And what typically happens is that many organizations tend to stuff additional ceremonies on top of that, right? So we have a problem with sharing information, for example. So let's do additional information sharing meetings. Let's do additional status meetings so that everyone involved is up to date and stuff like that. And in my book, that's basically just a way of kind of covering up the symptoms, not the real root cause, right? Because you really do want to keep coordination and meetings to a minimum. And the only way of doing that is to make sure that each team can operate autonomously, right? So that they can have this fit between an organizational unit and the actual architecture.
Yeah, I mean, I feel the pain already. I've been in, let's say, meetings only with coordinators, and we were like 60 coordinators where you think, this cannot possibly be true. We also have, like in a supplement material, of course, like screenshots, how you visualize those dependencies between teams. And I have to admit, when I talk about CodeScene, I used to talk only about hotspots, and I totally ignored that feature. So it seems to me that it's even, it's a more important feature. Or, is it more important? I don't know. But to me right now, it feels like it's something you should use in each and every project to really reduce your team dependencies.
Yeah, and I find it fascinating, particularly if we talk about stuff like microservices, right? Where we're very, very heavy upon measuring all kinds of things, right? We're measuring performance, we're measuring scalability and all that stuff. We have an alert system, right? But then we have these other architectural properties that are so important, like loose coupling, independent deployability, autonomous teams. And we are not really measuring that, right? So that's where I think behavioral code analysis can kind of fill that gap. And, it can work like a monitoring system, like an alert system for the architecture. And that's the way I've been using it over the past couple of years. And I have a very good experience with that.
And if, let's say, even alert triggers, what are the typical steps to, let's say, fix the problem?
So what actually surprised me the most, because it was so unexpected for me, that was that a lot of those problematic dependencies between different teams or coordination bottlenecks, very, very often the fix turned out to be technical. It's something we got wrong either in the high-level design or in the architecture, right? We stuffed too many responsibilities into one module, and now multiple teams have a reason to touch that module, right? Or maybe we do have a very modular architecture, but it's the wrong granularity on it. Maybe it's the wrong modeling concepts that we use. And very often it turns out that as software architects, it tends to be very common that we identify technical building blocks and we kind of build our architecture around that. And that's like more or less asking for heavy team coupling.
Yeah, I like that. Little code changes to fix big problems. I mean, little, but, usually if you have, I'm currently in a project with, let's say, 300 people, and it's incredibly hard to, let's say, without a data visualization on the coupling, to have a meaningful conversation.
Yeah, and I think that even minor improvements at that scale have a big, big payoff, right? Because imagine just the staff costs of 300 people, right? If you can say 1%, that can be quite some party, right? For that,
exactly. Yeah, I mean, coordination meetings with 50 people every once in a while, why not analyze the code base instead?
You could almost buy a private jet for that money you save, right?
Exactly. Yeah, from my perspective, I could have many more questions, but maybe let's close it here. Thank you, Adam, for the conversation. I can really recommend not only reading your book, but also check out the tool. Yeah, that's it. Thank you.
Thanks a lot for having me. A pleasure.
Thanks for listening to this episode of the GOTO podcast. Head over to gotopia.tech for lots more content from the brightest minds in software development.